The most common data structure in Haskell is the linked list. Here's an example. Let numbers equal the list 4, 8, 15, 16, 23, 42. Recall from your data structures course that a linked list is made up of nodes, each of which contains one element and a pointer to the next node. The next pointer in the last node is null. It doesn't point to anything. The functions head and tail let us look at pieces of a list. Head numbers gives us the first element, and tail numbers gives us the rest of the list. That's also a list, so we can ask for its tail. If we do this enough times, we get down to the empty list. Everything we've done has just been asking questions about numbers, not modifying it. It hasn't changed. In fact, Haskell data structures are immutable. They never change. It's as if they're written in pen. We're eventually going to be writing lots of functions that build lists. The most basic tool for doing so is the colon operator, which constructs a new list node. It is therefore sometimes called the cons operator. To make a longer list, just use cons several times. We don't need parentheses this time because, unlike most operators, cons associates from right to left. First 5 is consed onto the empty list to make a list of one element. Then 1 is consed onto the front of that list. Because Haskell data structures are immutable, it's okay for two lists to share the same tail. This could lead to nasty bugs in a language that allowed side effects, but it's safe here. On the other hand, arrays don't work well in a purely functional language. To get an array with a different first element, we'd have to copy the whole thing. Knowing how lists are represented helps us understand how long various functions take. Let's look at a few and classify them as constant time, where the length of the list doesn't matter, or linear time, where the time depends on the length of the list. Head takes constant time. Tail also takes constant time. Tail doesn't make any new nodes, it just returns the second one. How about length? This one takes linear time because the only way to tell how many items there are in a list is to walk down the list. Reverse numbers gives us the same list but backward. This requires creating new nodes, which takes linear time. The infix double exclamation point operator, pronounced index, gives us the element at a certain position in the list. Finding an element requires walking down the list, so it takes linear time. Specifically, the time is linear in the index. How about lastNumbers? Linear time. We have to walk down the list. Init gives us everything but the last element. This also takes linear time because we have to rebuild all of the nodes. The node containing 23 has to be a new one because it doesn't have the same next pointer as the old one. That means the node containing 16 has to be new, and so on back to the beginning of the list. Null determines whether a list is empty. Null numbers is false, but null empty list is true. This takes constant time. lm tells us whether a particular element is in the list. lm15 numbers is true. This takes linear time because we might have to look at everything in the list. How about the plus plus or concat operator, which concatenates two lists? This takes time linear in the length of the first list, which we need to rebuild. We can make lists of things other than numbers. For example, Haskell strings are just lists of characters. We can use comparison operators like less than on lists, and therefore to check the alphabetical order of words. The comparison goes through both lists, character by character, until it finds one with a lower value. This takes linear time. It is comparing ASCII values, so strictly speaking this is lexicographic order, not alphabetical order. All uppercase letters come before all lowercase letters. Lists of lists? No problem. You can probably guess what maximum and minimum do. These both take linear time, as do sum and product. Now suppose, like the young Carl Gauss, we want to add up the numbers from 1 to 100. This seems like a job for sum, but that would be an awfully long list to type in. Don't worry, Haskell's got our back. This is called a Texas range. It works for characters too. Want to count by twos? No problem. Counting down? That's about as far as we can take this. We can't use it to get, say, powers of 2, although we'll see a neat way to do that in the next video. There is one more neat trick, though. Are you ready to have your mind blown? What happens if we leave off the end of the range? I had to hit Control-C to stop that from taking over the world. That expression produced an infinitely long list. That may seem useless, but remember that Haskell is lazy. It doesn't evaluate things until the last minute. The take function gives us the first few elements of a list, even an infinitely long list. There are a few functions in this part of the chapter that I haven't covered: drop, cycle, repeat, and replicate, but you should have no trouble understanding them now. In the next video, we'll enter the fascinating world of list comprehensions.